Good morning. My name is Uday Bhaskar Pattapu, Associate Professor, Department of ECE, Space Institute of Technology and Sciences. So today I give a topic on wired and wireless transmission devices. The topic is wireless energy harvesting. So first of all, wireless energy harvesting. So in wireless energy harvesting means first of all rectifying antenna. Rectifying antenna means the rectifying antenna, also called as recna. It is used to receive microwave power and convert it to DC power. So rectifying antenna means antenna plus rectifier. So this is use of in free space RF signal received to DC power. So that is the process. Energy harvesting. Energy harvesting is the process RF energy receiving from different sources. So that energy the different sources and convert to electrical energy is known as the energy harvesting. Next, in rectifying antenna, main block diagram is first one is the receiving antenna, matching circuit, rectifier circuit, DC filter, and load. So a rectifier is the heart of the AC signal converted to DC signal. So receiving antenna. So to convert the RF to DC signal, main two kinds of technologies we should follow. First of all, how to maximum energy sent to the rectifier part. Second one is the how to rectifier efficiency. How to convert the rectifier efficiency. So first of all, receiving antenna. So in receiving antenna, we should follow the different types of antennas. So one is broadband antennas, circular polarized antennas, and also slant type antennas. So these type of antennas and also antenna arrays also. Suppose if you are using antenna arrays is the antenna receives the low RF signal also. One drawback of the antenna array is the antenna one drawback of antenna array is beam width is very less. Due to beam width is very less, so coverage area also less. Circular polarized antennas. Suppose if you are using circular polarized antennas, so in antenna receiving XY plane and YZ plane, both signal also receives the antenna. So that is the advantage. Next, wideband antennas. Suppose if you are using wideband antennas, so most of the frequencies we can receive the RF signal. So this is the process to receiving the antenna. Next, after the rectifier circuit. So in rectifier circuit, generally rectifier circuit we are using the nonlinear devices. So nonlinear devices, one of the drawback is it produces the harmonics. Suppose an rectifier part is produce the harmonics, these type of harmonics re-radiate the antenna. So whenever re-radiate the antenna, surrounding objects will electromagnetic interference will occur. So due to this problem, we due to this problem we design one filter circuit. So the filter circuit is that is useful for suppress the all the produced harmonics. After then, for efficient conversion purpose, DC filter we are using. So output of the rectifier circuit we are using DC filter. The DC filter blocks the RF AC signal, allows the only DC. So by antenna design, so I am considered as the planar slant antenna. This type of antenna, this antenna is radiate both the planes, XY plane and YZ plane. So this is the advantage to radiate the signals both the planes. So this is the monopole antenna. Ground slotted. So antenna is radiated different harmonics. Antenna is radiated different modes of the frequencies. So our antenna, this antenna is designed at our concentration is 2.45 gigahertz. So rest of the frequencies, these are the spurious frequencies. These frequencies are unwanted frequencies. First of all, we have to suppress these spurious frequencies. Because of if you have this type of frequencies will occur, antenna receiving all the frequencies. So electromagnetic interference will occur. We maximum efficiency conversion purpose suppress these spurious frequencies. One frequency is in between 3 to 4 gigahertz, another frequency in between 5 to 6 gigahertz, one more frequency at 8 gigahertz, and one more 9 to 10 gigahertz. These are the spurious frequencies. Our original frequency and fundamental frequency is the at 2.45 gigahertz. So this antenna is works at the Bluetooth applications. So design of antenna. Design and antenna we consider the FR4 substrate. Because of FR4 substrate is the cost is less. So thickness is 1.4 mm. Relative permittivity is 4.4 gigahertz. Sorry, 4.4 and last tangent is 0.02. how to suppress the harmonics. So in previously suppress the harmonics, different frequencies there. So I want to suppress the all the frequencies. Red color indicates the original antenna, conventional antenna results. So I have to suppress the all the frequencies. Here we follow the different techniques to suppress these spurious frequencies. So whenever suppress these frequencies, 2.45 gigahertz, this frequency does not disturb. So how to suppress these frequencies? Here two techniques is there. First of all, design the filter. Design the filter RF front end. Front end, we design one filter, so you can suppress the harmonics. Whenever you are using the RF filter, circuit complexity is high. So circuit complexity high means it takes more space. So that is the space point of view. That is the drawback. So how to suppress these spurious frequencies? So another technique is the whenever we are using the stubs and DGS means defected ground structures. So these stubs and DGS act as a filter. Due to that filters, we can suppress the harmonics. So here I am using the two stubs, suppress the harmonics purpose, S1 and S2. Suppress the harmonics, suppress the spurious harmonics. So we are using the first of all stub. Stub is considered as the S1 stub. This is the stub S1. S1 stub is considered the stub one length. S1 is the stub that is designed at feed. So whenever stub length S1 is increased 1.8 mm to 5.8 mm. So 1.8 mm to 5.8 mm, the at lower harmonics, the lower harmonics has been suppressed. So that is a red color is the red color indicates the original antenna results. A black color, S1 is 5.8 mm, the S1 length is the 5.8 mm. At 5.8 mm, these harmonics are suppressed up to the 7 gigahertz. Higher harmonics will existed. Higher harmonics exist, at lower harmonics has been suppressed. So how to suppress the higher harmonics? So for suppression of higher harmonics, another again one more stub is given, S2. So the S2 length is initially 3.85 to 1.65 mm. So that means this is at red color, black color. So this black color. So optimized of S1. This is the red color one, red one. So after then we are using the stub length is 3.85. 3.85. So this black one is harmonics are suppressed at frequency in between 5 to 6 gigahertz. At frequency in between 5 to 6 gigahertz, some more harmonics has been obtained. So in ground side, this is the front view, this is the back side. Ground side, beneath the feed, we consider as the U-type DGS. DGS means defected ground structures. U-type DGS we are using. So optimize the length. So here consider as the length C1. This is the C1 length. So vary the C1 length. So parametric analysis of the various C1 values. So up to this one, up to C1, harmonics has been suppressed completely. Up to four harmonics, up to 10 gigahertz harmonics is suppressed, except the fundamental harmonic. Next, surface current distribution of the proposed antenna. Suppose antenna is designed at 2.45 gigahertz Bluetooth or Wi-Fi application. So whenever using at 2.45 gigahertz, antenna is radiated entire portion. So main portion is this type of slot and this type of slot and also ground slot. So whenever using suppressing the harmonics at 4.9 gigahertz, 7.35 gigahertz, 9.8 gigahertz, so these harmonics has been suppressed. So due to S1 and S2 DGS. So at different frequencies at 4.9 gigahertz, most of the electric field intensity at this portion only. So at second one, 7.35. At 7.35, responsible for the completely stub 1 and 9.8 gigahertz. 9.8 gigahertz also stub 1 and stub 2 and DGS. By using these stubs, harmonics has been suppressed completely. So this is the fabrication design for the slant antenna. So this is we are using the FR4 substrate. This is the copper portion. This portion is the FR4 substrate. This is the front view. This is the back side. So back side is the slot is and U-type defected ground structure has been used. So measured results. So compared to simulated and measured results. So measured results agree with the simulated results. So at higher frequencies, little bit variation is there. So because of that is the soldering effect of the soldering, due to that one, at higher frequencies not agree with the simulated results. So compare with the simulated and measured radiation pattern. So almost uh, simulated and measured radiation pattern is same. Co and cross polarization is a little bit high because of antenna is receiving signals and transmitting the signal XY plane and YZ plane, both the sides. Next one, at the 2.45 gigahertz frequency, the gain of the antenna is the 3.5 dBi gain, So this is the YZ plane and XZ plane, radiation pattern at YZ plane, radiation pattern at XZ plane. YZ plane means at pi equal to 90 degree, azimuth angle is 90 degree, elevation all. Second one is XZ plane, elevation angle is 0 degree, theta is all. So antenna has been designed and suppress the completely harmonics up to fourth harmonics. So antenna gain also 3.5 dBi gain. So harmonics also suppressed. So that is the fruitful for our experiment. So next part, design the rectifier circuits. So here design the rectifier circuits, different types of diodes available. So here I consider the two types of diodes. One is the HMSS 2850 and another one is the HSMS 7630. So these are the diode specifications. So the Schottky diode junction voltage is very less, and this type of diode HSMS 2850 breakdown voltage 3.8 volts. The HSMS 7630 breakdown voltage is 2 volts. So this is the internal diagram of the diode. So this is the LS is the series inductance, next RS series resistance, junction capacitance, so parasitic capacitance. So due to frequency, due to temperature, these parameters will vary, junction resistance and junction capacitance. So first of all, this is a diode equivalent circuit. So here in our rectifier portion, we consider as the voltage doubler circuit. So this is one capacitor, diode and capacitor. Suppose if input signal is given, first one is diode is considered as the positive half cycle. This one is off, this one is on. Diode is considered as the negative half cycle. This one is off, this is on. So both the cases, positive half cycle and negative half cycle, here work the both the sides. Next of all, how to find out the input impedance? Input impedance is the main parameter. Antenna output impedance is 50 ohms. This diode rectifier input impedance, if diode rectifier input impedance 50 ohms means that is a maximum power transfer to the rectifier circuit. Suppose in case impedance is mismatch, so energy is not transferred to the diode. Check this one. So here using diode is HSMS2850 diode. So this is a voltage doubler circuit. So this is the 50 ohms for a source, means RF cable impedance 50 ohms. If you consider as the frequency response of this voltage doubler circuit, consider the real and imaginary part. The impedance of the voltage doubler circuit is Zin equal to 19.6 minus 180.1 ohms. So that means this is the capacitive nature. 19.6 means resistive nature, minus 180.1 means capacitive nature. So here impedance is 50 ohm. So this part, impedance of the RF cable or antenna impedance is 50 ohms. So this is the input impedance of the rectifier circuit. Input impedance of the rectifier circuit. So input impedance of the rectifier circuit is 19.6 minus 180.1 ohms at load resistance is 1 kilo ohm. So this entire impedance matched with 50 ohm. So whenever matched with 50 ohm, maximum RF power enter to the rectifier part. So the frequency response of this voltage doubler circuit is whenever this plot is come to 2.45 gigahertz, that is matched with the 50 ohm. So next one, how to match this complex impedance to real impedance 50 ohm. So here we are using the Smith chart technologies. In Smith chart method, So this one is the source impedance. Source impedance is 50 ohm. This is considered here 50 ohm. Next, load impedance. Load impedance is 19.62 minus j 180.1 ohms. That is the load impedance. So this load impedance equal to source impedance. How to match that impedance? So here adding on series inductor. Here adding on series inductor, that is considered the L3. That is considered as the L3. So the inductor is 8.132. So whenever we are applying this 8.132 inductor, what happened? So here imaginary part is nullified. Imaginary part is nullified. So next 19 point, only 19.6 real part is there. So the 19.6 real impedance converted to 50 ohm. So after that again I used the parallel inductor 9.18, that is the L2. That is the L2. So after then series inductor L1. So now source impedance equal to the source, load impedance equal to source impedance. So now maximum power transfer to the load. Next, the frequency response of the voltage developer circuit exactly matched at 2.45 gigahertz. So the impedance of the rectifier 50 ohms at J 1 ohm. J 1 ohm means that is the complex nature, that is the we can neglect that impedance. So Zn equal to the almost equal to the 50 ohm impedance. So whenever antenna rectifier input impedance 50 ohm, antenna output impedance 50 ohm, max antenna receiving the RF power entire into rectifier part. So next, the simulated efficiency. So at frequent input power 10 dBm input power, the efficiency is almost 70, more than 70%. After then exactly matched with 50 ohm, exactly matched with the rectifier input impedance is 50 ohm. Next, this is another rectifier circuits. So here using the parallel one inductor, series another inductor, here using the monopole transmission line, sorry, quarter wave transmission line, quarter wave transmission line. So here consider as the at 2.45 gigahertz, 2.45 gigahertz, the black line is real part almost 50 ohm, the black part is almost 50 ohm, imaginary part, real part impedance. So frequency response of the rectifier, this frequency response of this rectifier circuit is, this is the Bluetooth application exactly matches 2.45 gigahertz, the impedance is 50 ohm. So this is the lumped matching rectifier circuit. So this one we are using the diode is the SMS7630 diode. So this one is the 50 nanohenry inductor, 80 nanohenry inductor, one more 10 microfarad capacitor. These are the wires to short the ground. So 47 microfarad capacitor also. This is the quarter wave transmission line. So whenever increase the input power, different load resistance, RL equal to 1 kilo ohm, RL equal to 2 kilo ohm, 3 kilo ohm, 4 kilo ohm, the efficiency of the rectifier circuits more than 70%, more than 70% at in between 0 to 5 dBm power, we are getting the blue line more than 70% efficiency. Next, so conversion, RF to DC conversion, this one is at in between 2.45 gigahertz, 2.45 gigahertz, maximum voltage is 1.6 volts. Because of here using the SMS7630, the breakdown voltage is 2 volts. So we are nearer to getting 1.6 voltage DC voltage. Efficiency is also 70% efficiency. So based on the simulated results, the rectifier has been fabricated. Here using the RF components, this one is the diode, this is the inductor, this is the capacitors, this is also 47 microfarad capacitor. So test this rectifier circuits. So here using the RF signal generator. This is the RF signal generator using breadboard at instead of load we are using a LED. So whenever you are using the power at 5 dBm power, so the LED glown. So at at 3 dBm power, at 3 dBm power, the efficiency is more than 50%. So, and one more thing, DC voltage is considered as the 1.6 volts. So previously designed the fruitful antenna, after then connected the rectifier part. So this entire part is considered as the rectina or rectifying antenna. So this antenna, one is the lumped element matching. This rectifier part is lumped element matching. This one is the microstrip matching. So previously backside one frequency selective circuit has been used because of 3.5 dB is the compared to less gain. So if you are using this FSS frequency selective circuit, this one is reflected at 2.45 gigahertz and transmits all the frequencies. Due to this one, antenna gain increase more than 7.3 dB again. Whenever antenna gain is increased, so that one receives the low RF signals also. Next, so measurement setup. We are using a signal generator. This is a signal generator. Power amplifier. So here using the on power amplifier. Next, horn antenna. Horn antenna for transmitting the signal from signal generator. So far field distance. We are using the far field distance. So no connection between this part and this part. So receiving antenna. Receiving antenna means whatever the design antenna is there. So this is the our antenna, rectifying antenna. And also at load side we are using the multimeter. At load we are measuring the output voltage. So in measurement results at input power 7 dBm, the voltage is 1.5 volts. One is the VDC Retina 3, one is the lumped element matching, another one is the microstrip matching. One is 1.5 voltage, another one is the 1.4 voltage something. So the efficiency of the rectina, one is the more than 65%, another one is the 50%. So lumped element matching gives the better results in this case. So how to measure the power? So here using the Friis transmission equation. By using Friis transmission equation, antenna is radiated the transmitted power. Our rectifying antenna receives the RF signal power. Based on that signal power, we are calculate the transmitting antenna again, receiving antenna again, transmitted power and received power. Lambda by 4 pi r whole square. This is the far field distance. So efficiency is equal to Vd square by received power into load resistance. Based on these formulas, we calculate the efficiency of our rectifying antenna. So these are the some. So for rectifier circuits, we are using a 2.45 gigahertz antenna. So for rectifier, we are using the HSMS 2850 and 7630. One is high breakdown voltage, another one is low breakdown voltage diodes we are using. So antenna has been suppressed up to all the spurious frequencies. That is the better to conversion efficiency. So RFDC conversion efficiency has been calculated using the Friis transmission equation. So based on entire antenna, first of all suppress the complete harmonics antennas except the